So we'll get to that in a second. Just wanted to remind you of the basic equations that we use for calculating dispersion in tubes. I guess I got rid of those slides the other day. But the equation that controls the variance in the distribution is actually the sum of these two terms. And generally speaking, in connecting tubing, this term is vastly dominant because in the connecting tubing you will always find that the linear velocity of whatever it is going to be enormously high compared to what the linear velocity will be in the column. If you take even a milliliter a minute and put it through a hole which has a diameter of 1/100 of an inch, it's really going to rip through that tubing. So this term is almost always entirely negligible. So we can use this then as the leading term and estimate the variance in distance units, the variance in time units of the peak at the end of the column, or the variance in volume units of the peak at the end of the column, end of the tube, these ways. And these three equations are easily interconverted from one to the other just by units. So let's do some calculations sort of representative of comparing gas chromatography and liquid chromatography. And the key difference here is that the diffusion coefficient in a gas is vastly greater than the diffusion coefficient of a solute in a liquid. I'm going to assume 100 centimeters of tubing. That was done more for convenience than anything else. Notice that all of these are proportional to the length, to the first power. So if you double the length, you're going to double the variance. They're all inversely related to the diffusion coefficient, and they're all related. These two, the flow-based ones, go with a fourth power of the radius. The distance-based one goes with the second power of the radius. That's an important difference. But seldom do we ever use that much connecting tubing because connecting tubing is just plain bad. and you're going to minimize it. And unless you've got an instrument that's 50 years old, it's going to be compact enough so that you only need maybe 20 or 30 centimeters of tubing. This is a typical flow rate for LC. For capillary GC, a typical flow rate might be more like 5 cc's per minute, maybe 10 cc's per minute of carrier gas. But let's not, we'll just use the same flow rate for both of them. Look at the numbers. The sigma of the distribution in GC, these are all in seconds. That's 9 milliseconds. 9 milliseconds. However, in a liquid, it's 9/10 of a second. And and that's all due to the 4 order of magnitude difference in the diffusion coefficient. The radius, you see, if we even change the radius a little bit, we have a gigantic change in the sigma. What does that tell you? Do you want to use narrow tubing or do you want to use wide tubing? You want to use the narrowest tubing you can possibly get your hands on. And as I said, it's proportional to the length of the column, so you want to make that as short as you can within reason. The compromise is usually you need a minimum amount of tubing to get from here to there, so you always use the narrowest tubing you possibly can. And getting tubing narrower than about 0.005 inches in diameter is half of that. It's very difficult, and what you find is that it plugs up very easily. So people tend to use slightly wider tubing so the stuff doesn't plug up. You cannot do that with a modern LC column. You cannot use 1/100 of an inch tubing. You've got to use narrower tubing, and you've got to put up with the possibility of its plugging every so often. So let's put this in the context of HPLC. This is the problem I gave you to work on. I'm going to start by calculating the time-based variance. So this is the variance of the tubing. So we're gonna break this down into parts. The first thing we're going to do is we're going to calculate the sigma squared of the column. The second thing we're going to do is calculate the sigma squared of the tubing. The third thing we're going to do is we're going to compute the total sigma squared. The fourth thing we're going to do is we're going to assume a Gaussian peak, and then estimate the half width of the column as 2.35 times sigma total. Strongly advised, if you haven't developed this skill yet, when you're solving a problem, don't start slinging equations around like mad people. Step, step, step. Go back to your high school geometry. How did you solve those high school geometry problems? Given to find, take it stepwise. Make the steps small. The smaller the step, the less likely a boo-boo. Okay, so let's work on this. So the first thing I want to do is calculate the variance of the column. That's going to be equal to the retention time squared divided by the number of plates on the column. The retention time is going to be the retention volume squared divided by the flow rate squared divided by n. If I put in 0.6 for the volume, that's milliliters, and 0.5 milliliters per minute for the flow rate, convert that to seconds. This is going to work out to be 1.036 seconds squared. Tip of the day number 2. Always write down the units of the quantities that you're calculating. Always. Your hand should fall off if you don't write down the units. If you want, we could calculate the half width due to the column alone, but I didn't ask for that. But that would be done very simply by taking the W1/2 equals 2.35 times the sigma of the column, which means we have to take the square root of that and multiply it by 2.35. And just for yucks, that works out to be 2.39 seconds. That's the first part. The second part is to calculate the sigma squared of the tube. I'm going to do that since I'm working in time units. That's the one in time units, so I'm going to use this equation. So it's pi over 24, r to the 4th, L over d times f. So the sigma squared of the tube in seconds squared is going to be pi times 2.608 times 10 to the minus 8 times 30 over 24 times 10 to the minus 5 times 8.33 times 10 to the minus 3. That's going to be seconds squared, and that works out to be 1.22 seconds squared. Here's the big step. Variances are additive. Standard deviations are not additive. This is by my tally, and I thought about this last night a lot, this is the 6th time I've said the equivalent of that statement in this room. So this is 1.036 plus 1.22. It gives me a total of 2.25 seconds squared, or thereabouts. And the corresponding sigma is the square root of that, which is 1.50 seconds. The width in seconds then is going to be that times 2.35, which works out to be 3.52. So look at this. If you didn't have any connecting tubing, the width of the peak would appear to be 2.39 seconds. Unfortunately, you do have to connect the column to an injector and a detector. And that's going to approximately increase the peak width by 50%. You are going to take a very, very serious hit in the appearance of that peak. It's going to be much wider than it really is. It's going to appear to be much wider than what it really is at the exit of the column. Use narrower tubing. It's already 1/100 of an inch. You could go to 0.005, and this term would go down a lot, because this is the seconds-based variance, or the volume-based variance. They go with the 4th power of the radius, not the square of the radius. And so if you went from 0.01 tubing to 0.005 tubing, it would go down 2 to the 4th power, which would be a factor of 16. And it would be completely and totally negligible. A small change can have a humongous effect on extra column band broadening due to the passage through the tubing, because of the damnable Hagen-Poisson flow. That's all that's going on here. Okay, now, even in an empty tube, you cannot apply the Taylor-Arris equation until the tubing has a certain minimum length. What you're looking at here is a computer solution of the time-dependent equations, and then a plot of the concentration of the solute coming out the end of the tube versus the volume of eluent that was used to push the fluid through the tube. So this axis is the volume of eluent used to push through the tube divided by the total volume of the tube. This number here corresponds to the number of theoretical plates that are in this tube. You want a lot of theoretical plates, that's going to give you a narrow zone. A lot of plates means the HETP is very small. If you have 1/100th of a theoretical plate, you get a wretched, wretched looking peak. The peak maximum occurs at a time corresponding to half of the volume of the tube, or volume corresponding to half of the volume of the tube, because the flow rate at the center is twice the average flow rate. So it moves through the tube twice as fast as the average. And so the maximum occurs in half the time. If the tubing is long enough, you have a general transition from this wretched looking tailed beastie on up to a very nice looking Gaussian peak. It does not take more than an inch or two of tubing to get from here to there, if you're even in the case of liquid chromatography, because the tubing you're using is so narrow that an inch could have 200 or 300 theoretical plates in it. The point of this is that it doesn't always work if you have really short tubing, but you'd never use tubing that short anyway. So the approximations that Aris and Taylor made are reasonable approximations, and their equation basically works under practical circumstances. In fact, the equation works so well that a lot of people measure diffusion coefficients in what's called an Aris-Taylor dispersion experiment. And this turns out it's much easier to measure diffusion experiments, especially in liquids, that way than any other way, because it's a fast experiment. If you got something that's diffusing with a diffusion coefficient of 10 to the minus 7 centimeters squared per second, you have to let it sit in that tube, stationary, a long, long, long time before you have something that has moved at all. But under the flow conditions, because of the parabolic flow and the inverse dependence on diffusion, the lower the diffusion coefficient, the bigger the effect, and the easier it is to measure the number. So it's a very accurate equation in the real world. There's one other issue that I didn't mention, but it's a real one, because more often than not, the tubing is not perfectly horizontal and it's not straight. You can't put 25 meters of GC capillary in an oven that's maybe about that big, unless you curve it. And if you curve it, you induce what's known as secondary flows. So this picture here is supposed to be showing secondary flows, and these are the flow streams, like this. And it turns out that these are good, because they effectively enhance radial mixing. And if they enhance radial mixing, they're going to oppose the broadening caused by the Poisson flow. But in order to get much help from this, the radius of the curvature has to be real small. It has to be small compared to the radius of the tube. On the order of 20 or less, you begin to get an effect. If it's 50 or 100 or 1,000, is an absolutely minuscule effect, which is actually the case most of the time. So we're finally going to get to chromatography now. Let's go back to the open tube, horizontal, laminar flow, all of that stuff I assumed to work the Aris-Taylor problem. Except we're going to put a stationary phase on the wall, and only on the wall, not in the middle of the capillaries, just on the inside surface. We're going to assume that is perfectly homogeneous, that it's a thin film, and we're going to do a mass balance. So we consider some element delta Z of the column of the tube. We got convection in, we've got diffusion in, we've got convection out, we've got diffusion out, we've got radial diffusion, but we have one other thing. I'll get to these in a second. We have one other thing going on. The solute is in equilibrium between the mobile and stationary phase. This is the stationary phase concentration at equilibrium. So what I'm saying is that as soon as the solute gets pushed into this little cell, it's going to start to move on its own towards the stationary phase, because it has to equilibrate with it. It's going to try to equilibrate with it. The simplest problem to solve is when it's always at equilibrium. And there are two things we have to assume in order for this equilibrium to exist. Number one, the kinetics of diffusion of the solute in the film are very fast. Now the film is some kind of gooey polymer, so this is not exactly true. The thinner we make the film, the closer to reality this assumption will be. There's another assumption, and it's a chemical issue more than a diffusion or a mass transfer issue. When a substance crosses an interface between a gas and a liquid, between two immiscible liquids, there's an interfacial impedance that resists the solute going from one phase to the other. We're going to assume that this interfacial process, anywhere in the system, either gas-liquid or gas-solid interface, we're going to assume that these are really fast, so that the solute is always in equilibrium between the mobile phase and the stationary phase. So this is the relationship we're going to assume between the solute in both phases. By the way, it's a very simple thing to show that K prime, which is equal to K, times the volume of stationary phase over the volume of mobile phase. If we assume a thin film, K prime is 2 times the film thickness divided by the radius of the capillary, times K, this equilibrium constant for distribution of the solute between the two phases. So here's the old problem that Arris and Taylor solved the other day for an empty tube. But we don't have an empty tube anymore. We've got a stationary phase, and the solute is in equilibrium between the two phases. So I really have to consider this term. Now, if Q is in equilibrium with C, I can replace Q with simply K times C. And now I have to take the time derivative of an equilibrium constant times the concentration. Well, an equilibrium constant has no time dependence. It's a constant. So you can do that. So you have K times dC dt, dQ dt, plus dC dt, dC dt, dC dt plus dC dt. Well, that's just K plus 1. That's not a problem. This doesn't make the equation any harder to solve at all. It's the same problem. The solution to the problem is that the zone velocity is equal to the average mobile phase velocity down the tube divided by 1 plus the retention factor. Which means that the retention time, which is equal to the length of the column divided by the zone velocity, is going to be 1 plus K prime times L over the average velocity of the mobile phase. If we set K prime equal to 0, we get the same thing as for an empty tube. That's sort of obvious. However, we have to modify the Arris dispersion coefficient by multiplying it by all this stuff. And this comes out of the solution of the differential equation. The differential equation now has a K prime dependence. And when you turn the arithmetic crank, this is what falls out of it. So we now have a dispersion coefficient which depends upon diffusion coefficients, depends upon velocities, and also depends upon how much retention you have. And when we convert that to an HETP, we get an HETP that now depends upon the retention factor. This is real chromatography. And we'll see in a few minutes what this stuff does to the chromatography. Before I go there, I want to show you some real chromatograms. Well, not chromatograms, real Van Dienter plots. This is with a glass wall-coated open tubular column. The stationary phase is OB101. That's like saying it's plain vanilla. That's just an everyday run-of-the-mill permethyl siloxane phase. It's 25 meters long. The diameter, the ID of the capillary is 0.25 millimeters. The film thickness, this OB101 thickness, is 0.4 microns. That's a very thin film. Very, very thin film. The analyte here is heptadecane. Column temperature is 175 degrees. And under these conditions, the retention factor of the heptadecane is about 5. And it doesn't matter which gas you use, you will get the same retention factor. And the reason is that under these conditions, the gas phase is ideal. Now, something you learn in general chemistry is that in ideal gases, there are no intermolecular interactions in ideal gases. Therefore, the nature of the gas cannot possibly influence retention. So all three of these curves correspond to the same retention degree, the same retention factor. But we see big differences between the curves. This is the nitrogen curve as the carrier gas, the helium curve, and the hydrogen curve as the carrier gas. Which gas are you going to use? Nitrogen?
I use hydrogen.
Why?
It has high linear velocity. You can use a high linear velocity, which have with low HETP.
Say it another way, the optimum velocity is higher in hydrogen than in helium than in nitrogen. There's not a huge difference between hydrogen and helium. Nitrogen, clearly, forget about it. And this is the way people do things nowadays, is they use hydrogen, especially since helium is getting more expensive. The hydrogen is not a serious safety concern unless you break the tank open. The flows of hydrogen here are extremely low. I've not heard of a GC blowing up. I'm not saying it can't happen, but okay, back to this equation. Let's look at the limits of this equation at low K prime and high K prime. If I set K prime equal to 0, I get the Aris-Taylor result. If I set K prime equal to the largest possible value, the coefficient of the C term goes up and up and up and approaches an asymptote. And at infinite K prime, it becomes 11/24. So there's an 11-fold increase in this contribution to the HETP as K prime gets bigger and bigger and bigger. And that means above K prime of, let's say, 20, there's not much further change. You're already at the limit of the second term, the C term, versus retention factor. It starts down there. It doesn't start at 0. It starts at 1/24, and then it goes up to 11/24 somewhere out here. And you can see there's hardly any change between 25 and 20. But there's a serious increase as K prime goes up. that would lead you to think that you want to work at low K prime. But that would be a really, really, really bad idea. And I'll show you why it's a bad idea. But we got one more issue to deal with before we get there. I had to make a big fat assumption to get that equation. I had to assume perfect equilibrium between the mobile and stationary phase. What if I had a thicker film? Diffusion in that thicker film could be slow. You might have to use a thicker film because the retention might be too low, and you put more stationary phase in, and you can jack up the K prime. But eventually, it's going to get thick enough so that you have to consider the kinetics of transfer between the stationary phase and the mobile phase. And that's done by writing this kinetic relationship between the stationary phase concentration and the mobile phase concentration. And Ka is the adsorption rate constant, and Kd is the desorption rate constant. Just like we were talking about a week ago in the random walk problems. It's really not different than that. The problem, though, is we have to solve this equation simultaneously with the partial differential equation corresponding to conservation. And it's a challenging problem, but it can be solved. The HEPT that results is exactly the same first two terms as when we assume equilibrium. But there's a new term that corresponds to this slow transfer in the stationary phase, and it's 2k prime over 1 plus k prime squared average velocity divided by the non-equilibrium constant, the Kd, the desorption rate constant, the rate constant for the solute to get out of the stationary phase, out of it. Now, if we assume that that process is purely 100% diffusional, and there's no interfacial kinetics involved, which is generally the case, we can calculate this rate constant from diffusion theory in a thin film. So we're going to just assume a flat, thin film. And that works out to be 3 times the diffusion coefficient of the solute in the stationary phase, divided by the square of the film thickness. So this Kd has units of seconds to the -1. Because we got centimeters squared per second in the numerator, and we got centimeters squared in the denominator, so it's seconds to the -1 rate constant. So we're going to substitute this Kd in there. We're going to put it in there, and we'll get this equation. This is exactly the first two terms as before, and now we have 2/3 k prime over 1 plus k prime squared, same as that, except it's 2/3, not 2 anymore. The film thickness squared divided by the diffusion coefficient of the solute in the stationary phase times the average velocity of the mobile phase. All right. Here's the problem. Here's the problem. Diffusion in gases is really fast. So this guy is really big. But diffusion in liquids is 4 to 5 orders of magnitude slower, even for small molecules. And the stationary phase film in gas chromatography, more often than not, is a polymer. Very, very viscous. Diffusion in the higher the viscosity, the lower the diffusion coefficient. So this could be 5 or 6 orders of magnitude smaller than that. Now, the only way that's not going to kill us, I mean really beat us over the head, is if the film is very, very thin. So micron dimension films, even if the capillary is half of a millimeter ID, you would still only use a micron film probably at the thickest. And in what we call a high resolution capillary, that film would be only a few tenths of a micron thick to make this pretty, I can't say negligible, but, or insignificant, but minor, but minor. Now, if I convert this whole thing to reduced units by defining h, a little h is h over r, and nu as u bar times r over d, and to be crystal clear, we're going to use d of the mobile phase. If I do that, then the reduced equation looks like this. And I'm going to rewrite this reduced equation, especially this term right here, by defining a new parameter, theta. I'm going to define theta as the ratio of the film thickness to the radius of the capillary, that ratio squared, times the diffusion coefficient in the mobile phase divided by the diffusion coefficient in the stationary phase. So I'm going to take that and plug it in to the previous equation. And I get 2/3 k prime over 1 plus k prime squared theta times the reduced velocity. So this term depends upon theta, which is effectively a reduced film thickness. Now we can start to look at this in terms of nice simple plots. Oh, forgot one more thing. If, when you go to exceedingly thin films, like 1/10 or 2/10 of a micron, you start to pick up some sensitivity to slow interfacial kinetic effects. And the slow interfacial kinetic effect depends upon the film thickness and the rate constant for crossing that interfacial barrier. That's a chemical rate constant now. You can't really predict what it is. It depends on exactly what the solute is. It depends upon what the stationary phase is. It depends upon the temperature. So I can't do any more with it than this. I can't predict it. But you're only going to see this contribute to the HETP when you've got very thin films. Okay. One more issue before we get into real chromatography. What I've been talking about so far is a wall-coated open tubular column. But there's another kind of column called a porous layer open tubular column, also pronounced a plot column. And it's exactly the same thing, except on the wall of the tube, they impart a high surface area etch the inside of the capillary and grow whiskers in there. And they're trying to get a higher surface area and make the wall have a higher surface area so they can put more stationary phase in there without making it a thicker stationary phase. See, if you have a high area and you put the same weight of stationary phase on a high area, the average thickness has got to be less than if you put it on a smooth surface. So the idea is you get the benefit of the stationary phase without paying for it in terms of a thick film. Does it work? Sometimes. Is it expensive? Yes. But sometimes it's indispensable. Okay, so let's get into what the effect of all of these damn parameters are. We're just going to look at the effect of the retention factor on the Van Deemter. We're going to assume that the kinetics are infinitely fast. That means theta is 0. Complete and total equilibrium. There's what you get if k prime is 20. If I make k prime factor 2 smaller, that's what you get. If I go to a k prime of 3, that's what you get. K prime of 1, you get to there. K prime of 0, you get to there. You can't do any better than that. Which one's going to give you the most plates on a given length of column? The one with the lowest HETP. K prime 0. And you can see that these are approaching a limit. And if I went to k prime 40, it would hardly be different than k prime 20, except there'd be twice as much retention. Here's the flip side of that. I'm taking k prime equal to 1, and I'm going to start with equilibrium and then make it slower, 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 slower. Or you could think of this as infinitely thin film progressing towards a thicker film as I make theta bigger. So there's the infinitely thin film. There's a theta of 1, 2, 3, 4, 5, and I quit at 5. You can see there's a big gap between the 3 and the 5. It just gets worse, gang. It's not like the k prime thing where it reaches a limit. It just continuously gets worse and worse and worse. If you look at the curves carefully, you'll see that the optimum is really shifting. And for the thick film, the optimum flow rate has shifted in. Here's the optimum flow rate with a theta of 0. And of course, the minimum HETP has gone up quite a bit. So clearly, you want a thin film. This is the reverse of the plot. We're going to calculate plates per meter. I'm going to assume my solute is hexane, my carrier gas is hydrogen, 100 degrees centigrade, 1 atmosphere pressure, and I'm dealing with a very, very thick, a very high diameter capillary. There's K prime 0, 1, 3, 3, 10, 20. Again, this is pointing you towards using not much retention, because there's your best plate count. Here's the bugaboo. I'll quit right now. That's K prime 1, 3, 10, 20. I didn't plot K prime 0 because the effective plates, if K prime is 0, is 0. Here's K prime 0. There are no plates. If you don't got retention, you get no resolution. You get no effective plates. The point of this is that you've got to compromise between having low retention to give you good HETP, but you've got to have enough retention to get the separation to happen. You're always fighting this effective plate curve. But it turns out that your best results are really with a pretty high retention factor. But it doesn't make much sense to go beyond K prime 20 because the curve is going to be just a little tiny bit above it. So there's definitely an optimum range in K prime. If you go too low, there's not enough retention. If you go too high, you pay too much in time for the analysis. We'll never be able to do an analysis like this again, because for no other case of chromatography do we know enough to predict what the HETPs will be without a lot of fudge factors. I mean, a lot of fudge factors. But this effective plate would still apply conceptually. There's a best retention factor to use. Sorry for running 5 minutes over.